When faced with a complex math problem, our first instinct is usually to power through it using brute force calculation. We count, we add, and we crunch the numbers until an answer falls out. But sometimes a problem has a specific geometric structure that lets us skip the heavy lifting entirely, if we know how to look at it. Think about the famous Rubin vase illusion. If you stare at the center, you see a single continuous object. But if you shift your mental framing to the negative space, that exact same silhouette instantly resolves into two human profiles facing each other. This is the shape created by the fourth iteration of the square buildup algorithm. It looks like a jagged, complicated diamond, and counting its unit squares row by row takes some time. This jagged perimeter resolves into a predictable pattern once we change our orientation. To find that simpler geometry, we have to stop reading the shape horizontally. Instead, let's rotate the entire figure exactly 45 degrees and focus entirely on the diagonals. In this new orientation, look at the longest vertical columns. Because this is the fourth iteration, so n equals 4, there are exactly 4 of these columns, and each one is exactly 4 squares tall. Now look at the alternating shorter columns interlocking between them. These are always exactly 1 square shorter, so length n-1, and there are exactly n-1 of these columns too. By identifying those two sets, we can pull them apart. When we do, the complex, jagged fractal resolves into two perfect, independent geometric planes, a 4x4 square and a 3x3 square. Visually and logically, the total number of squares simplifies to a straightforward mathematical sum, n squared plus the quantity n-1 squared. This gives us a clean geometric equation. But if you remember from our earlier row-by-row calculations, the total number of squares is defined by the polynomial 2n squared minus 2n plus 1. So how does n squared plus n-1 squared prove that exact same formula? Take a moment here. Pause the video, grab a piece of paper, and try to manually expand the binomial n-1 squared on your own. To expand it, we set up the FOIL method. First, outer, inner, last, multiplying the binomial n-1 by itself. Multiplying the first terms gives us n squared. The outer terms give negative n, and the inner terms give another negative n. Finally, negative 1 times negative 1 is positive 1. Combining those middle terms, we get n squared minus 2n plus 1. Now we just add back that original n squared from our larger magenta square. 1n squared plus another n squared leaves us with our final combined polynomial, 2n squared minus 2n plus 1. The abstract algebra flawlessly verifies the physical separation we just performed on the shape. We've now mapped this shape in 3 completely different ways. First, we stacked horizontal rows of squares like bricks, adding the sums of odd numbers. Second, we tracked its growth over time by adding iterative rings around the outside. And finally, we twisted the spatial fabric of the shape itself to reveal the 2 hidden squares intersecting on the diagonal. Despite traversing 3 entirely different logical and visual pathways, all 3 methods arrive at the exact same destination. As those different physical representations fade away, the math remains. This polynomial describes the constant properties of the construction. Whether we count by rows, rings, or diagonals, the mathematical result remains the same.